Hey guys, this is, or hey Dr. Olga. This is our team for the May 318 lab final project on the electric vehicle speed control with Catherine Alcazar, Atul Kutanja, Khalid Almuteri, Ratisha Das, which is me, Yosef Alamari, and Mason Brigham. So our objective of the System Dynamics and Control Lab was to utilize all the material learned during the duration of the course to act as engineering consultants to our client Solco to meet all of their design requirements. These design requirements include the following bullet points. Just note that the rise time needs to be more than 0.1 seconds and the setting time needs to be less than 0.2 seconds. Our control design process involved these steps of modeling the system analytically, planning the design specifications, design controllers computationally, conducting experimental studies, and iterating as needed. Those initial parameters that I talked about with the rise and settling time is addressed here. These were some of the guesses that we used with a certain MATLAB tool, and with those tools we were able to find the PID controller equation, and here we see the rise time is greater than 0.1 and the settling time is less than 0.2, just like what we needed. These are the calculations from those original values, converting that polynomial essentially to the KP, KI, tau F, and KD values, which is our gain values. And we're going to vary each of these values to see the patterns in what our step response and like our responses are. So here we varied the KI from 0.01, 18, and 40. Notice that with the 0.01, our rise time is super high for a low KI. And what that means, it takes a long time for it to get up to the value that we want. We want the value of 12, but as you can see with the low KI, it doesn't even get close to there, and we need to go for a very long time to even approach 10. With KI 18, this seems to be an optimal value because while we have a lot of noise about that value of 12, we see the KI getting there, and then KI equals 40, we just have a lot of oscillation, a lot of crazy sort of things, and we know KI equals 40 is way too high. With a KP value, we tested for 0.001 to a 10, and notice that as it increases, we experience less crazy sort of wide oscillations, but then with like a super high value like 10, we're getting a lot of like more consistent jagged sort of response. 2 seems to be an optimal value. While it oscillates, it does oscillate more closely to the desired value of 2. With our KD value, we tried a couple of different ones to kind of check what would happen if we varied like from a middle sort of value to a high value. Notice that 0.001 and 0.05 seem to give us some optimal sort of options, but 0.001 gave us a super high jump at the very beginning, which we wanted to avoid, so we tried to mediate for that by increasing it to 0.05. 2 basically causes it to oscillate to 20 multiple times, or just like big different values multiple times, and KD equals 15. If it was let on for a longer amount of time, we would see that it was taking a longer time to oscillate about 30. This is a tau F. Please note for that these graphs, there was a mistake and we weren't able to catch the fact that our KP value was the wrong value. But our tau F of 0.1 is the most optimal value. The other values are oscillating a lot more. We're seeing also just an increase in oscillation because one of the values are incorrect, but tau F 0.1 did give us the best sort of response. And so this is the best that we have with KP equals 2. Oh, sorry, I misspoke. But in the last slide, it wasn't that KP value was wrong, but the KD value was wrong. KD was too high. We had accidentally kept it as 2. So if you notice in the like graphs or code for the Arduino. And so in this one, KD is the correct value, KI is the optimal value, KP is the optimal value, tau F is the optimal value. And if we were trying to minimize sort of that initial peak that you see, but it wasn't really getting much better than this, and so we kept it the way it is, and these are the best combo values we got. So these are customer recommendations for different types of controllers. You have some pros, helping reduce steady state error, improving the slow response over damp system for a P controller, and you can read the rest sort of, but these are just different kinds of controllers. We did work with a controller. And then we're hoping to use these applications in future directions in the aerospace industry, home appliances, electric vehicles, and robotics. Thank you so much, and congratulations, Dr. Olga, on your PhD. Defense. Bye.
Nice. Thank you.
Yes. We're still